Okay, today we're going to start our lessons on the trigonometry of a right triangle. So this covers the integrated algebra standard AA42, which is find the sine, cosine, and tan ratios of an angle of a right triangle given the lengths of the sides, and AA44, which is find the measure of a side of a triangle if you're given one of the acute angles and the length of another side. Okay, so our vocabulary today is hypotenuse, adjacent, opposite, sine, cosine, and tangent. Okay, and actually sine and cosine, oftentimes we see these words abbreviated as this, sin and cos, and tangent we see it abbreviated as tan, but these are the full names for them. Okay, so the first thing I want to go over is a quick note about labeling. When we have a triangle, and especially in a right triangle, we can either label the triangle by angles or we can label it by sides. Okay, the tradition is that when we label it by angles, we put capital letters on all the angles. Okay, so for instance, I have angle A, angle B, and angle C in this triangle right here. And if we label it by sides, what we do is we draw a line from the vertex of A, and the side that it hits becomes lowercase a. Okay, likewise with C, we draw a line from the vertex of C, and the side length that it hits is lowercase c, and the same with B. Now, in a right triangle, recall that there are two side lengths that are not the hypotenuse. Okay, and we call these the legs. There are two legs in a right triangle, and the longest side is called the hypotenuse, and it's spelled that way. Okay, the hypotenuse is always right across from the right angle. So a note about this is always across from the right angle. Okay, so the side lengths in the legs in the right triangle and the hypotenuse as well can be labeled two different ways. So if I want to just speak about this leg right here, I can say that it is both line segment BC and line segment AC. Okay, I can also say that it is length A. Okay. All right, so let's get into the trigonometry. Trigonometry is just ratios. Okay, they're just, and make a note of this, they're just ratios of side lengths. That's all these are in a right triangle. You'll see trigonometry again in Algebra 2 and in pre-calculus, and it will be a little bit more complicated than this, but for right now, what we're talking about is very simple. Now, in a right triangle, there's the right angle that's labeled with the square, and then there's two acute angles, A and B. Okay, so A and B are always acute because it can't be more than 90 degrees because you already have one 90-degree angle. So for right now, let's just focus on A for a minute here. All right, let's not focus on B. If we focus on A, then the side lengths, if we focus on A, we can name all the side lengths in relation to A. All right, so there are the side lengths that make up the angle A, and if you recall, an angle is made up of two rays or two line segments that meet at a common vertex. So these line segments that I've labeled in yellow meet at the vertex A. Okay. Now these two line segments are going to be called something. One's going to be the hypotenuse, and the other one's going to be called the adjacent. Right? And then the line segment, the leg of the triangle that doesn't make up part of A is going to be called the opposite. Right? The one that's labeled in pink is the opposite. Okay, so line segment BC is the opposite of A, and line segment AC is called adjacent to A. All right. Now, the adjacent side means it's part of the ray that creates the angle, but it's not part of the hypotenuse. All right. Now, if we focus on the other angle B, so let's say that this time instead of focusing on A, we're focusing on B. Everything gets labeled differently. So here's the other acute angle B. Now, these are the side lengths that make up B. Okay. Now, the adjacent is no longer AC like it was for acute angle A. Now the adjacent is BC. And the line segment that's opposite B, or the leg of the triangle that's opposite B, is AC. And this is an important thing to understand because there's not just opposite and adjacent are relative. They're not. When we say opposite and adjacent, it's going to depend on the angle that we're looking at. So we're always going to have to focus on what the angle is, and then we'll be able to find the opposite and adjacent. Right? There's not just one of each in a right triangle. Right? It just depends on the angle that we're looking at. Okay, so when I take the sine, all right, and I put sine in its longer version. Okay, we often abbreviate it as SIN, but this is the full name for it. It's a Latin word. Okay, probably translated from an Arabic word, and actually I think Wikipedia says it may have been mistranslated from an Arabic word. But when we look at the sine, it is a ratio of side lengths. Okay, and it's going to be the length of the side opposite the angle, and it's going to be over the hypotenuse length. Okay, so if I focus on angle A, right, and I always have to indicate, I can't just say sine is equal to something. No, the sine is a function that takes in an angle. The input of the sine function is an angle, and what it does is it gives you back a ratio side length. So I say, okay, sine of A, I want to look at the opposite angle. So I draw a line that's across from A, and I say, the opposite side length. So the opposite side length is 3, right? Now the hypotenuse is always going to be the same. There's only one hypotenuse in a right triangle. So the opposite over the hypotenuse will be 3 over 5, and that's it. It's just a ratio of side lengths. Now if instead I focus on B, then the opposite's going to be different. The opposite's going to be the leg that's right across from B, so that's going to be this one. So the sine of B is going to be 4 over 5, because 5 is always the hypotenuse. Okay, so those are the two. So if someone says sine of an angle, you just are looking for the ratios of side lengths. Okay, cosine, and this is the longer word cosine. Cos is the abbreviation of this longer word cosine. Again, this is a Latin word. So the cosine of an angle is the length of a side adjacent to an angle over the hypotenuse. Okay, so if I look at angle A, the adjacent side to A is going to be the side that makes up the angle of A, but that is part of the angle A, but it's not the hypotenuse. So this right here, this green one, is always going to be the hypotenuse. Okay, now if I look at the side lengths that are associated with the adjacent angle, that's 4. And the hypotenuse is over 5. So the cos of A is 4 over 5. Okay, if I just switch my focus and I focus on B, the adjacent angle to B is going to be this line segment BC. So the cosine of B is going to be 3 over 5. Right, one interesting thing to note here is that the sine of A is the same as the cosine of B. Okay, and if you look back here, the ratio that was the sine of B, that's the same as the cosine of A. Okay, so that is something that you should write down. The sine of B is equal to the cosine of A, which is the other angle. The cosine, or the sine of A, is equal to the cosine of B. Okay, now we get to the tangent ratio. The tangent ratio, and again, this is a longer word right here, this is the abbreviation. That's going to be the, I actually mislabeled this. This should be the opposite side length over the adjacent side length. Okay, so tan of A, so if we focus on A, the opposite would be 3, And the adjacent to A would be this, again, it's the line segment that makes up A, but it's not the hypotenuse. Okay, and the tangent of B, so let's get rid of that. The tangent of B is going to be the opposite, which is 4 over the adjacent of B, which is 3. Okay, and so notice that these are reciprocals of each other. So the tan of A is going to be 1 over the tan of B. And likewise, the tan of B, this goes without saying, is 1 over the tan of A. Okay? All right, so let's get some practice. Oh, and the one thing that you might have heard from older relatives, if you've ever talked to them about trigonometry, is that they use this phrase here, sa ka toa. It's a mnemonic device to remember the ratios. This is that the sine is opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And the tangent function is the opposite, over the adjacent. Okay, so it's a quick mnemonic device to remember what the ratios are. So I'm writing it down in all the corners here. So let's start with one of the problems that we have here. Now, the one thing is, before we solve for all the trigonometric ratios, we're missing a side length here. Okay, so we're going to have to use Pythagorean theorem to find that side length. So if you recall, and actually let's call that b. So I'll call that lowercase b. If you recall, a squared plus b squared equals c squared in a right triangle when c is the hypotenuse and a and b are the side lengths. Okay, if I square the lengths of the sides and I add them together, if I square the lengths of the legs and I add them together, I would get the hypotenuse squared. So we're going to use that theorem in order to find what b is. So if I solve this formula for b, I would see that b squared is equal to c squared minus a squared. I'd subtract a squared on both sides. Okay, and so b is going to be the square root of c squared minus a squared. It's a quick way to do that. So we look at b is equal to the square root of, it's going to be the square root of c squared, which is 2 times the square root of 7 squared, minus a squared, which is this one right here. That's a squared, or that's a. So I want to square the square root of 6. Okay, let's finish up our calculations up here. 2 times the square root of 7 squared is 2 times the square root of 7 times 2 times the square root of 7. 2 times 2 is 4. The square root of 7 times the square root of 7 is going to be just 7. So this becomes 28. And the square root of 6 squared just is the square root of 6 times the square root of 6, which is just 6. Okay, so this becomes the square root of 28 plus 6. So that is the square root of 34. Right? And let's think about this. Does it have any, is there any other, are there any perfect squares in there? 34 is 17 times 2, and 17 is a prime number, and so is 2. So this is as simplified as it gets. So b is the square root of 34. Okay? So I'm going to erase some of this so that I have a little space to find my ratios here. All right? That's the first thing to do. So solve for all the side lengths using the Pythagorean theorem. Of course, you don't erase this in your notes. You want to keep that in your notes because you're going to have to do these problems tomorrow. All right, so once you found that, it's fairly easy to use this mnemonic to remember. So sine of a, so if we focus on a, is the opposite over the hypotenuse. So we have the square root of 6 over this 2 times the square root of 7. Okay, and the sine of b is going to be the opposite here, which is the square root of 34 over the hypotenuse is 2 square root of 7. Right? Now, we don't like to leave square roots in the denominator, so we're going to simplify this by multiplying these by the square root of 7 times the square root of 7. Okay. Now, 6 times the square root of 7 will be the square root of 42, because remember, we can put them both together under the same radical sign. And on the bottom, 2 times square root of 7 squared is going to be 2 times 7, which is 14. Okay. And let's see, 42 is 6 times 7, so there's no perfect square that we can pull out there. Okay, and here we want to do the same thing, so we want to say that this is times the square root of 7 times the square root of 7 up here. So this becomes okay, that's 218 over, and 2 times, this would be 14, right? Because it's 2 times 7, this becomes 7. Okay, and if you think about the prime factorization of 218, it came from 2 and 34, but 34 was, sorry, it came from 7 and 34, but 34 was 2 and 17, so all these things are prime factors, so there's no way to simplify that any further. Right, so there's the sine of A and the sine of B. Now if I find the tangent ratio, the tangent is the opposite over the adjacent. Okay, so the tan of A is the opposite, which is, oops, that's the square root of 34. The opposite, which is the square root of 6, over the adjacent, which is square root of 34. I'm going to do that trick again. Okay. So this becomes the square root of 204 over 34. Now the square root of 204, actually you can pull a 4 out, so this becomes 4 times 51, which becomes 2 times the square root of 51. Okay, so this can actually be simplified a little bit further here. This is 2 times the square root of 51 over 34. Okay, the tan of B is going to be the opposite here over the adjacent, which is square root of 6, so it's square root of 34 over square root of 6, but we want to rationalize the denominator here. So this becomes the square root of 204 over 6, which is, remember, that is 2 over 2 times the square root of 51 over 6, which can actually be reduced because 2 and 3 reduce. 2 and 6 reduce. This becomes a 1 up here, and that's a 3. So we have the square root of 51 over 3. Okay, and this actually could have been reduced a little bit further as well. 2 square root of 51 over 34 could be reduced to 1 over 17. Or square root of could be reduced to the square root of 51 over 17. Okay, now the cosine of A becomes, let's see, so cosine is the adjacent over the hypotenuse. So we have adjacent is this angle right here in A, so it's the square root of 34 over the hypotenuse, which is 2 square root of 7. All right, now actually, you know what? We don't even need to figure that out because we said that the cosine of A is equal to the sine of B. So the sine of B gets us was square root of 218 over 14, okay? And the cosine of B is the sine of A. So that would be square root of 42 over 14, okay? So that's all of our ratios. All right, let's try another problem here. Okay, we have another triangle where we're missing one of the side lengths here. So we want to find that side length using the Pythagorean Theorem. So if we recall, B is equal to the square root of C squared minus A squared. So we are going to do, so B is equal to, let's see, the square root of C squared. So C squared is, so it's the square root of 97 squared is 97, minus, that would be 64. Oops, that's 97 minus 64. All right, and that gets you the square root of 33, and there's no prime factors in that, so let's just write that here. Okay, so let's find our ratios here. The sine ratio is the opposite. So sine of A is opposite, which is here. So it's the square root of 33 over the hypotenuse, which is the square root of 97. Okay, let's rationalize this. Okay, and this becomes the square root of 3,207 over 97. Okay, sine of B is, and again, if you think about the prime factorization of 3,207, it's going to be 33 and 97. That's what I multiplied to get that. And 97 is a prime factor, and 33 is 3 and 11. So there's no perfect squares that I can pull out of that. Okay. All right. So the sine of B is going to be opposite of B, which is 8, over the hypotenuse, square root of 97. That becomes, if I rationalize the denominator here, multiplying it by that, it becomes 8 times the square root of 97 all over 97. Okay. Now I can actually fill in these, right? So that's 8 times the square root of 97 over 97 for the cos of A, and the cos of B is the sine of A, so that's square root of 3,207 over 97. Okay. Now the tangent of A, the tangent is the opposite of A over the hypotenuse. Oops, let's see here. I sort of erased our... Okay, so the tangent of, let's see, the tangent of A is the opposite of A, which is square root of 33 over 8. And that's already the denominator is already rationalized, so we can leave it like that. And the tangent of B is the opposite, which is 8 over the square root of 33. And so this one we will have to rationalize. This becomes 8 square root of 33 over 33. Okay. So in the interest of time, I am not going to do this problem. Actually, why don't you write this problem down and try it, and I'll come back. I'll work on it without off the video, and you can come back and check your answers in just a minute. Okay, and so I did the hypotenuse length, and I got 5x because I squared 4x and 3x. I got 16x squared, 9x squared. I add them together to get 25x squared, and the square root of that is 5x. And if you look, it's a 3, 4, 5 right triangle with an x attached to it. Okay. Now to get we're actually going to have to label these because I forgot to label them. So to get the sine of A, I have to look at the opposite, which is 3x over the hypotenuse, which is 5x, and this just reduces to 3 over 5 because the x's cancel. The sine of B is 4x over the hypotenuse 5x, which is 4 over 5. Okay, and then we can fill in these. And the tan of A is going to be the opposite over adjacent. So opposite here over adjacent, which just is 3 over 4. And the tan of B is the reciprocal of that. Okay, so it's pretty easy when you don't have any square roots and you don't have any radicals.